So we're just going to look at how to finally graph complex numbers. Now, we already graphed some trig stuff with like sine, cosine waves, tangent, slope waves, right? And we looked at the imaginary numbers, add, subtract, multiply, divide. We're going to kind of combine those together in the last part of Chapter 7, where you're converting a lot of stuff to imaginary numbers and graphing complex numbers all together. Okay, so just to start off, reminder of what the relationship is between complex numbers and imaginary numbers. Okay, so know that complex, let's see if I can do this. Complex numbers have two parts. Okay, they have a real part, a real number that is, and they have an imaginary part. Okay. So the imaginary part, the I part, is really just a subset of a complex system, actually a complex number system, right? That consists of a combination of a real number and an imaginary number. And we can graph these. Now, it's going to look very familiar of how you graph just regular old x comma y. It's basically the same rules, but the axes are different. Okay, so let's just sorry. Instead of the Cartesian plane, we call it the complex plane, right? And it looks similar. So if I just draw a standard old what looks like an xy axis system like this, right? It starts off looking like anything you've graphed since like 7th grade, right? Just x comma y, y equals mx plus b. However, the axes are not x and y. What we're going to graph on the horizontal is the a value, which, notice how we don't call it x, but we call it a, which stands for the real number. So that's right here. Okay. And then on the vertical axis, we're going to graph the b value, which is the imaginary. All right, that's this part. So together, we're graphing the two parts of a complex number on the same graph, right? So we are graphing complex values just like this. Okay? So it's a little shift, right? And you can't mix up x for a and y. I mean, while they look like just two lines intersecting, they mean entirely different things, right? But it is convenient that it's a familiar setting, so we can actually adapt what we already know and graph these pretty quickly. So, for instance, if we want to graph 2 minus 6i, we just have to identify, well, 2 is the real part, right? That's the real number, which goes on the a-axis, right? So I just have to find 1, 2. And then negative 6 is the imaginary part. So I just have to know how to find negative 6 on this axis, which it's still down, is negative 1, 2, 3, 4, 5, 6. Which means the complex number, 2 minus negative 6i, right, is right here. So basically, if you really want to break it down, into familiar terms, we just graphed 2 comma negative 6. Okay. That's what we just graphed. So, in a sense, the values and the numbers and how you do all this are essentially the same. Now, here's the kicker, though. It's going to change a little bit, and you're going to find out that these are not just points in space like we've graphed before, but they're actually vectors coming from the origin, which means it has a direction and a magnitude. Right? And when you guys start doing problems, especially in physics, about all sorts of wind, current, things like that, particles moving through space that have some gravitational force and they can be moved. Those are vectors, things that are traveling at a certain speed or velocity at a certain direction, and then some gravitational pull takes it and moves it a certain way, right? That's all vector work, right? So the study of it and the practice of knowing vectors are actually really important. So that's what this all touches upon, right? And that's why it's not just a little point in space, but it actually has a little more meaning behind it. We're not going to get into a lot of that yet. There's a whole chapter on this stuff later, though. Okay? Right now, it's just the beginning, the bare bones, right? So if we can get this much today, great. We're in good shape, right? We don't have to go any further. So take a gander at number 1 over here and give it a try and see if you can duplicate those results. Alright, so you should have something that looks like this. Here, roughly. If you're already thinking like, well, there's got to be something more to it. Well, start thinking about, just by looking at the complex number, can you figure out what quadrant the vector will end up in? Start thinking of those terms, because that's what it was always about. The first questions in Trig was, okay, what quadrant are we in? What's positive, what's negative, right? Stuff like that. All the similar questions that you've already answered before are going to be asked again, just with this format of the question, right? Written in this complex form. So that's where we're heading, right? So if you can duplicate your results from prior, work, then you're on the right track, right? If you start doing I wonder if it acts like the same thing as we did before, right? And you start making those connections, then you're on the right track. Part of the analysis part of math analysis is connecting of what we've already done. It's kind of similar to what we've done in the past, and just finding the little parts that are different, but realizing a lot of it is pretty much the same, right? So if you learn the foundations really well, the rest of it falls into place a little easier. Okay, so that's basic graphing. You'll do a little bit of that. Not too bad, right? We know that they're A and B axes, not X and Y. One's the real number, one's an imaginary number, and that a complex number consists of 2 parts, a real and an imaginary. Technically, an imaginary number can be a complex number. For instance, if I just told you, like -3i, say, well, is that complex? You'll say, well, there's no real number, right? But the real number could be 0. This could be 0 minus 3i. So even imaginaries in themselves are also complex numbers, technically. There's a whole debate that goes on and on about that, right? So now, the next part is that you guys saw a little while ago, we started multiplying a lot of imaginary numbers, and I had you do like, 2 plus 3i, and you squared it, and then you had to do a bunch of work, like, 2 plus 3i, 2 plus 3i, right? Some of you did this box thing, and you had to go through all this work. Right, we got 6i, 6i, and then we found any I squareds turn into negatives, negative 1s. So this really came out to -5 plus 12i, right? Well, there's going to be a graphical way to actually do this. That's why we're looking at this. So what happens if you put these 2 vectors on a plane and do some multiplication, right? Second of all, what if I said, well, I want you to find what 2 plus 3i to the 6th power is? Well, that means we'd have to take this and then multiply it once again by, 2 plus 3i, right? And do the whole thing over again, and that would be to the 3rd power. Then I'd have to do it again for the 4th power, again for the 5th power, again for the 6th power. And then I'd finally be done, hoping I didn't make one little clerical error along the way and still get the right answer. So it'd be very tedious to go through and find what 2 plus 3i to the 6th power is. So we have this other format, which we call trigonometric form. Okay? And this trigonometric form offers us a whole different path linked to the trig we've already learned, and it links all the imaginary number rules and all the trig functions and unit circle rules you already know, and it makes this seamlessly easy, right? So the first step of that is actually converting it to the new form. And then the rest of the week, you'll learn how to multiply, learn how to divide, learn how to raise to a power, learn how to take a logarithm, right? All that good stuff. So, how does that work? Start off with just a basic first quadrant axes here. All right, and generic values, let's say A and B. Okay. Remember, this is the real, this is the imaginary. And we have some angle theta here. We don't know what it is. We can use a little trig to come up or represent these values, but using trig, right? So if this is the height here, we know that's considered like the y value, so that's this value, right? And let me be consistent. What was I using before? Purple. And this, the run, would be the a value. Right? So how can we write these a and b but using some trig? So we'll think about, we have this other value, r. So we can use our good old friends, opposite over adjacent, adjacent over opposites, all that good stuff to represent these values in a different way using trig. So the first one I'll show you, the second one you'll probably figure out just by pattern. Right? So let's say I want to write a. Right? So if I want to write a as some trig value, my likely go-to would probably be a over r, which is the, with this angle as a reference, a over r would be the adjacent over the hypotenuse, right? So what trig function is adjacent over hypotenuse? And confidently you answer cosine, right? So cosine of theta equals a over r. And if I just want to have a by itself, because I'm trying to find out, well, what does a equal, right? By the way, if you ever hear in terms of, like I want to write in terms of a, that means get that value equals. So in terms of a means get a equals, which you might have to solve for a. In this case, multiply both sides by r. All right? So from this, I know that a equals r times whatever the cosine of theta is. That's what a equals. Remember, a is the real part. So we just figured out how to write the real part of a complex number using trig. Okay? Now, what do you suppose we would do for b? what would B equal? Well, over here, a reference to this angle, B is the opposite. So why not use opposite in hypotenuse? What trig function would that be? All together now? Sine, 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 everywhere sines. So that would be opposite over hypotenuse. Now this may not be complete overwhelming to you. You're like, okay, I get it. But it took a very long time for someone to come up with this method. And it busted open the doors for future mathematical study just by rewriting the problem in a way that made a little more sense. Okay. So now here's what we can do. We have our what we call our rectangular coordinates, the things that we're used to graphing the same old way, and we convert them to trigonometric. All right. So what I'm going to do is substitute. So wherever there's an A, I'm going to write that instead as r cosine theta. So if I want to find the real part of any complex number, I'm really just going to multiply the radius times the cosine of the angle we're working with. And then any B values, I'm going to write instead r sine theta. Now don't forget we have this I over here floating just to remind us that this is the imaginary part. It's the phone dropper. And you'll notice that we have an R in both of those. So if we factor the R out, right, just take that out, we end up with this R in front. And we're left with something called the trigonometric form of the complex number. And for different types of problems, the I is written afterwards and the I is written before. In this sense, when we're using the trigonometric form, we put the I in the front. So we could say R times the quantity of cosine theta plus I sine theta. That's how we'd actually say this out loud. So the tools that we're using and what we're applying are not just kind of made up, here are the rules, but you could actually quickly derive them yourself and figure them out. If you remember that the x-coordinate is like the run, that makes a big difference. You notice how the A, which is the left and right, which is like the x-coordinate, right, is first. It's like the x-coordinate. It's cosine, right? The run has always been cosine. The rise has always been sine. So there's a lot of familiar patterns that are all sticking out here. That's important just in case you get lost and you can't remember something or why. Well, which one comes first? Is it sine or cosine? If you actually know how this works, you don't have to memorize it. It'll just make sense, right? A lot less thinking when it's something actually just makes sense to you. Right? That's why we take the time to show you all this, as opposed to, okay, here's a formula, just do it this way and get an answer. Show me you get the same answer I do. Right? That wouldn't be a whole lot of thinking. And then by the time you get to the next quiz, you're like, wait, this is too much to memorize. That's the key. If you're trying to memorize it, it's too much work, right? Easier to pay attention and know why something works. Then it just makes sense, okay? So our goal today is basically, given this form, right, rewrite it into the trigonometric form. So we have to figure out what the radius is and what the theta is. That's where that unit circle comes into play. So let's just look at a few of those, and this will speed up pretty fast. Okay. So looking at this, negative 1/2 root 3 over 2. As we saw before, you want to be thinking what angle comes from these two values, right? Where the cosine, or the x value, is negative 1/2, and the sine is root 3 over 2. And your knowledge of the unit circle right now will make this problem quick or drawn out, right? So how many of you right now could say what the angle is associated with those coordinates? Right? Give yourself a little mental test right now. If it comes to you, you could figure it out in about 10 seconds. You're probably in good shape. If not, you're still like, if you know it's like a multiple of 30, you know it's not the 45s because those were all over 2s. Okay, that's good. You know it's not the multiples of 90. Okay, that's a little bit better. Do you know what quadrant this is in? Just by looking at that, what quadrant are we looking at? That's definitely in 2. So all the familiar questions we've asked before, they still work, right? So now you're like, okay, this is a multiple of 30 in the second quadrant. That leaves me with 2 options, 120 or 150, 2 pi over 3 or 5 pi over 6, right? And then a quick reference just to make sure. Sure enough, yeah, negative 1/2, comma, root 3 over 2 is 2 pi over 3, 120 degrees. So the faster you can associate these coordinates with the actual angle, the easier your quizzes and tests are. This is the same quiz you guys took on the first and second week of school, just making sure you know the unit circle. So if you need to, go back to those assignments, get refreshed, get quicker on them. Promise your quiz and test grades will, get 1 out of 2. Sorry about that. Still 2 pi over 3. All right. Radius is still 1. Try that again. So we got cosine of 120, even better, plus I sine 120. That's one way of writing it. Another way of writing the same thing would be, of course, in radians. Now, as far as which one you know how to write it in, go with the directions. If it's not stipulating the directions, ask, or like if the answer is like on your homework or in the back of the book, look at the format of the answers, the odd answers that are in the back of the book. See how they're written and just keep that pattern through all your problems. Chances are the default is radians, but degrees are used an awful lot more. I know at the beginning of the school year, it was basically all radians all the time. Now it's going to be a little mixture. You just want to be comfortable with both, right? All right, next. All right, any clarifications from this, other than it's 120, not 150? All right, if you feel good, go ahead and go to B. Try that. First, identify what's the radius of this, because it's not 1. So what is the radius of this? And we didn't do this on the last one, but it might be good to graph it. So if you graph it, maybe you could figure out the radius geometrically, right? Instead of analytically by thinking about the value. So where would negative 3i be graphed? Now if it helps, I mentioned this earlier, think of it as 0 minus 3i. All right, so where would that be on the graph? What angle does it make? All right, so negative 3i would be 1, 2, 3. There's negative 3i. This is B. It's right there. So what is the radius? Well, if I made a circle out of this with the origin, what would the radius of the circle be? Yeah, 3. Yeah, that's all. So if we're given some 90 degree or pi over 2 increment, right, we could get the radius straight from the graph. So that's nice when that happens. So that means I know, so far, this much information. Right? I know that much of my answer, and the only remaining part is to find out what that actual angle is. So what is the angle? That's the next part. Helps to know a unit circle, although you might not need it for this one. That is, if, of course, you don't overthink it. What angle is this? In degrees? If not, look at your unit circle. What angle is it? Yeah, don't overthink it. You know the answer already, right? So it's not designed to be tricky. Trust me, you've already done the hard work of memorizing it. So trust yourself. It's not going to be tricky to you. Now, true or false, are these two numbers always the same? For now, yes, they're completely always going to be the same. So if you have one for here, it's going to be the same number here. Don't have to bend your brain over that. Now, can you write this a couple different ways? You guys saw in different tests and quizzes, it says, okay, write this in 3 different ways. Right? That's always been an ongoing theme, is multiple representation. So what's another way you could write this? You guys come up with them. I'm tired of talking. You tell me one or 2. Negative 90. Very nice. Yeah, we got our old friends. Negative 90. Forget the I. There we go. What's another one? Once you get the other one, you could probably get one more after that. Think units. 3 pi over 2, yeah. Yeah. And then ultimately you could say, well, if I could do 270, which is like 3 pi over 2, and negative 90, what's the radian equivalent to negative 90? You could say negative pi over 2. Yeah. So lots of different correct ways of writing the same thing, which is important because occasionally you guys will come up with different answers and say argue over which one's right, which one's wrong, when really they're both correct. Or all 3 here, 4 here are correct. Let's not forget that on our graph this was an actual vector. Didn't put that in. Alright, so leave you at that. Yeah, that looks good. By the way, if the radius seems unattainable, if you're like, I can't figure out what the radius is, you can always use Pythagorean theorem. So if you have the A, let's say like here, I just don't know what I can't figure out, I didn't recognize it was the unit circle by looking at these numbers. You could always say, well, A squared plus B squared equals C squared. A and B are now real number plus imaginary number. Real number squared plus imaginary squared equals the radius squared. Right? So you could go through, I'm telling you this because it's on your homework. Right? You could go through and find and calculate the radius the old-fashioned way. Right? That equals r squared, which means we just take the square root. And you could figure out by plugging this in your calculator, it would just come out to equal 1. Right? If you want to do that, if you need to do that. Because not all the numbers are going to be these nice 30 degrees, 90 degree increments, right? They might be something else. So there's a way to find the radius in every single case, and it's just our old friend Pythagorean theorem, nothing more. All right, now the second half is just reversing the whole process, right? So just reverse the process and start with the trigonometric form and go back to the complex form here. Right. So if you know the cosine of 330 and the sine of 330 back from your trig table, then that's probably the biggest hurdle. Right, so what is the cosine of 330 degrees? That would be 11 pi over 6. If you need to, take a look at it. What's the cosine of 330? Again, you probably recognize it's a multiple of 30, so it's either going to be root 3 over 2 or a 1/2. What quadrant are we in? Fourth quadrant. So what's positive, what's negative? Right, all the same questions, right? What's positive? X-coordinate. What's negative? Yeah, so technically this is going to be a minus, not a plus. All right, so if you get the signs down first, then go to here, look at your 330. It's root 3 over 2, comma, negative 1/2. Where'd you go? So we have root 3 over 2 minus I sine, times negative 1/2. Well, we already got the 1/2 negative in there, so minus 1/2. This just turns into a basic distributive property. So multiply by 2, multiply by the radius. So of course, when you multiply these together, 2's cancel out. Root 3. And you multiply these together. 1/2 times 2, of course. 2's cancel again. So we'll have negative 1i. Negative 1i. Which, just like in standard algebra, we usually don't write anything with a coefficient of 1. We don't write 1x equals. We just write x equals. So we can drop the 1 and just say it's root 3 minus I. The question is that if you're given this as a question, could you work it backwards and come up with this? That it's this angle and it has a radius of 2. Right? You're like, well, how would I get a radius of 2? And that's where you can draw the triangle, right? If you know it's in the fourth quadrant, you could say that this is root 3, this is negative 1, and you could do the Pythagorean theorem and you'd come up with the radius here equal to 2, right, by doing the root 3 squared plus 1 squared equals r squared, right, which would be 3 plus 1 . So we want to be fluid with going back and forth between this complex form, trig form, and all, everything in between. All right, so give 3 a chance, and then we'll be done. So pi over 2. You can look back or recall. It's 0, 1, cosine and sine. Remember x, y, cosine and sine. So that's how I know my cosine is 0. Right? What's the x-coordinate of a 90-degree angle? It's still 0. What's the y-coordinate of a 90-degree angle on a unit circle? It's 1. So we're just using all that stuff we already know. It all lies back on that unit circle. So on top of doing this basic homework here, which is, pretty straightforward, maybe revisit your biggest concern will be not relying on this on your homework. So maybe use it in the first few, and don't use it the rest of your homework so you really, really, truly know if you got this down. So for some of you, this might be the hardest part, is going back and remembering and studying this. So on top of your homework tonight, practice this. If you find out, like, I'm just too rusty, there's a chance that I could take probably an easier one of the quizzes that's going to come up because of this, but I can mess it all up because I just don't know my unit circle well enough. And then something that you'll see people, like the unit circle quizzes we had at the beginning of the year where people are just getting 100%, 100%, 100%. You might be that one that's like getting 6 out of 12 just because you didn't study the unit circle enough. And all your problems subsequently are now going to be incorrect answers simply by not knowing the multiplication table of higher math. Right? So practice that. And it doesn't take a lot of effort. It only takes, probably 3 times through that speed test. It'll come back to you if you've already done work in the past.